Okay. Hi. I hope you're doing well. Everything going good. Today I'm going to look into a curiosity of mine that I had for some time, and I try to look into it a bit deeper, and yeah, I think it's a good topic. It's an interesting topic, and at least for me, I don't know, maybe I'm looking at it from the outside, it looks nice, but we're gonna find out anyway. So yeah, let me see if I can. Okay, so there are a couple of links. This one, also this one. Okay, let me also. I'll also send it in the chat. Hi today. Okay, so this is the. Oops. This is the paper. And okay, so basically there's one paper and there's one blog post that I think the first time that I ran into it was in the blog post. And yeah, it basically has an interesting idea, at least the way that I understood it. Is that basically when you're talking to LLM, you always provide some context, and in this context would be a process using the LLM, and then in the end, would return some response. So yeah, most of the LLMs, most of the language models, you pass the context as input, and then they kind of try to they kind of process the entire context, and then because of these attention mechanisms, they process the entire context, and in the end they spit out of course some output. And then I ran into this paper, and also to just mention it, I don't really study that, like I don't read that many papers to be honest, but this one was kind of interesting for me because I really like the idea. It basically looks at the let's see if I can just okay, and then and so they propose this recursive LLM, and in general it kind of looks as a it treats the long prompts as part of the external environment. So basically they allow the LLM to kind of programmatically examine or like kind of digest the context, and doing so they don't have to process the entire context. Yeah, and also it's kind of really interesting for me because I think maybe if you are working with some hardware that you don't have a strong computation power, then processing the entire context would be kind of wrong, and or like kind of not feasible in a sense. And basically looking at things in a programmatic way is kind of interesting, and it kind of allows to process many long contexts. For example, they also here they have the benchmarks, or for example even with 1 million token, and you can see, for example, they kind of managed to, using this the recursive language model, they are able to process the entire context and kind of keep the score in the different, especially in the longer context, for example with 1 million context. And also we have the code. It says that RLM Qwen38B outperforms the underlying Qwen by 28%. Yeah, and then it also might even hit the GPT-5 like capability with and some long context tasks. So in general, I think it's really important to realize that this is only like 8 billion parameter model, and they were able to kind of achieve the GPT-5 score for some of the long context tasks. Of course, this is also in the direction of the specialized models, I would say. So there's a chance that these general purpose models, they kind of improve day by day, and they keep improving, but maybe there is some use case that you kind of need maybe 1 million token to just pass in as the context, and you don't want to process the entire thing. Basically, there would be some models that they cannot process the entire thing. So and also this is a really pretty recent paper, to be honest, and I'm kind of curious how it's kind of how people build upon this, and if there would be some practical examples coming out. Okay. And they also, okay, give me a second, let me they also mention it on 3 long context tasks, and I'm kind of curious to look at the data sets, to be honest. Okay. Effectively process up to yeah, they also, for example, in this paper, I just ran into it, they do this SFT, like supervised fine-tuning, and for example here they say that they kind of are able to process 500,000 tokens, so they kind of extend the model capability in a sense. But for me, still but that's also the question. For example, for me, if you for me, it makes something like a little bit makes more sense to work with the this RLM idea and kind of dig into the context. But for example, here they kind of need the they need SFT. Of course, there's training, and also I think in the RLM, this recursive language models, there was also training. But in the end, I think the context would be kind of processed anyway. So for example, here if they put 512,000, like 500,000 token, this 500,000 token would be processed anyway. Okay. So yeah, for me, this one is still, of course, it has some novelty, but the problem is they fine-tune the model and they fine-tune the model, and the model has to process the 500,000 tokens anyway. But here, the smart thing is that they don't do this. They don't process the entire context. We scale the input from 18 degrees significantly. So yeah, they scale the input length, and GPT-5 performance degrades significantly as a function of both input length and task complexity, while the RLM maintains a strong performance, and inputs beyond the red region do not fit into GPT-5 context window, but the RLM handles them effectively. Additional experiment across other models and benchmarks are in 3. So these parts, they don't even like 500,000 token and 1 million token, they don't fit on GPT-5. Resulting not only in empirical gains but also additional theoretical expressive power compared to vanilla transformers. Though most inference time methods for dealing with long contexts are task specific, the most popular general approach is context condensation or compaction, where context from user requests or agent trajectories is repeatedly summarized once it exceeds a length threshold. Ultimately, compaction is rarely expressive enough for tasks that requires dense access throughout the prompt. It presumes that some details that appear early in the prompt can safely be forgotten to make room for new content. We introduce RLM, a general purpose inference paradigm for dramatically scaling the effective input and output length of LLMs. The key insight is that arbitrarily long user prompts should not be fed into the neural network directly, but should instead be treated as part of the environment where the LLM is tasked to symbolically and recursively interact with. As Figure 2 shows, an RLM exposes the semi-external inference. Okay, I'll be right back. Okay. Oops. Okay. Okay, an RLM exposes the same external interface as an LLM or a reasoning model. It accepts a string prompt of arbitrarily structured and produces a string response. Given prompt P, the RLM initializes a read eval print loop programming environment in which P is set as the value of a variable. It then offers the LLM general context about this REPL environment. And permits it to write code that peeks into and decomposes P, and to interactively observe any side effects from execution. Crucially, RLMs encourage the LLM to understand, transform, and execute the input prompt by writing symbolic programs that invoke the LLM itself, and as many slices of the input as necessary. Okay. By treating the prompt itself as an external object and enabling symbolic recursion, RLMs tackle limitation of expressive power in recent work on coding agents, retrieval agents, and sub-agents delegation. In particular, prior coding agents and retrieval agents treat some designated external data source, for example file systems or corpus of search document, as an environment for fetching snippets. However, that can only fill up the underlying LLM's context window with snippets before breaking down. So he also mentions this coding agents, retrieval agents, and sub-agents. Similarly, prior self-delegation approaches allow LLMs to invoke themselves as sub-agents. However, they are handicapped by the underlying LLM's limited output length, because they are designed to verbalize subcalls auto-recursively rather than producing them programmatically. We evaluate RLMs using a frontier closed model, GPT-5, and a frontier open model, Coin3 Coder, 480p. Yeah, this is the 48 billion parameter, and I think for every prompt, or like every token, I think only 35 billion is activated. So this is like the mixture of experts or something like this, if I'm not mistaken. Across 4 tasks with varying levels of complexity. They look into deep research, information aggregation, code repository understanding, and synthetic pairwise synthetic pairwise reasoning task, where even frontier models fail catastrophically. We compare RLMs against direct LLM calls, as well as context compaction, retrieval tool, use agents, and code generation agents. We find that RLMs demonstrate extremely strong performance even at the 10 million plus token scale. Holy shit. And substantially outperform all other approaches at long context processing. I mean, this is I think crazy, because I think at the moment there is not a single language model that can process 10 million tokens, and it would be like super crazy if you can just say, okay, I have, I don't know, a file or some documentation that has a length of 10 million tokens, and then I just paste it, or like let the model know that this is the file that it should dig into, and then the model would just try to like shred it into smaller pieces and tries to kind of do a surgery on the context and to just get the results that it wants. I mean, for me it's super I mean, this would be like closer to the intelligence that I have in mind. Like, for example, if I say artificial intelligence, I think this would be a closer thing to it, rather than just pasting everything and yeah, that in the end like everything would be processed. So here it kind of smartly, I mean, at least from my understanding so far, it kind of tries to find the structure of the text. It kind of tries to break things down. I would say this might be closer to the artificial intelligence that I want to see. It doesn't process everything blindly. Maybe this is one important part, at least for me. But it's crazy, to be honest, if you ask me. Like 10 million token scale. Yeah. And substantially outperform all other approaches at long context processing, in many cases by double-digit percentage gains, while maintaining comparable cost. Yeah, this cost is also, for me, is a bit part of like it can also be really important, because I mean, there is two sides of things. One of them is that I use these recursive language models to just be able to look into bigger context, and I just get this feature kind of using these recursive language models to just be able to look at the context that I cannot look at with other language models. So like other like vanilla language models in a sense. And this is one approach, like one feature that this recursive language model gives me. And the other one would be that, okay, you want to process 10 million tokens. That's like a huge cost, or at least maybe you can deal with it once, but also the accuracy kind of is questionable. And I use these recursive language models to try to reduce the cost. So basically one feature would be you are able to do something that you would not be able to do with other typical language models. And the second thing is that it kind of costs less than the traditional language models. But that's a question, like it says comparable cost. My question is like, how does it compare to that? I mean, it's also a bit hard to really compare. Maybe we can see some comparison for this region, where, for example, the GPT this white region, that GPT kind of can process such input length. For example, with this, I don't know, 100k or like 200k or something. So here there's a chance that we can see the comparable cost, like the same task, and both of the language models, they can handle it, and the idea is that which one kind of costs less. Yeah, let me also have a look at this diagram here. Okay, it says recursive language models treat prompts as part of the environment. It loads input prompts as a variable inside a REPL environment and writes code to peek into, decompose, and invoke itself recursively over programmatic snippets of the variable. So let's have a look. So we can also do this. Okay. Yeah, so here. I can also maybe change the music a bit. Okay. So we have this RLM, and then okay, so the the start, and then we have this environment that we saw here. Is it? Yeah, here, and the prompt is kind of from the environment, like it kind of acts as the part of the environment, and it says that you're reading an extremely long book. Can you list out all which items that were made before the blah blah blah? Yeah, before the great example, let's say before the great catastrophe, and then chapter 1, and then it just starts. So the model can just say, okay, I want to print the first 100 characters, and then it kind of splits the parts into part 1 and part 2, and then it says in chapter 1, find all items that are listed to belong to people with blah blah blah. So it kind of calls the LLM query, so it kind of calls itself. It's like it created a new prompt and it gave it to a language model again. And also these, both of them, they kind of are at depth 1. And then it will get some response, like the silver flask, blah blah blah, and then Herod's ring, and so basically it kind of broke down the entire book into 2 parts, chapter 1 and chapter 2. And then the final answer, it says that from chapter 1, Bob was the only character that was noted to be alive and carrying a flask before the great catastrophe. In chapter 3, Alice uncovers a ring belonging to the fallen King Herod. Anyway, so it kind of broke down the context. It kind of understood the structure of the text, and it just called the underlying model. So basically you can say that it's kind of like the to some extent it's like tool calling, but one of the tools is again a language model. So I think I also have used the idea that you ask another language model as a tool call to give you some answer on a specific context, but of course it was not in this context. It was not to kind of dig into the context or anything like that. But I think in a very high level you can kind of think of it that this is just a LLM which has a tool, that the tool is basically another LLM. And then there's this Python environments, of course, that they have access to. I'm kind of curious that how did they implement this Python environment. I think this also would be some thing that we have to look into. I kind of want to also read the chapter 2, and then we can maybe have some look in the code, because I'm also interested to dig in a little bit more to see what is what. Okay, so not gonna lie, I kinda, my eyes are a bit irritated because of the monitor today. Okay, given a base neural language model M with maximum context size of K, a recursive language model is an inference time scaffold around M that treats the user prompt as part of the environment without giving up the ability to densely process its content through different calls to M. So again, it's like the same model. The model, it has a context. If the context is too much to handle, like if the length is too much to handle, then it's probably gonna use another set of the language models to get the answer. And I'm also curious because regarding the processing of these small calls, because the context would not be not really looked at unless if it's like a really small context. For example, let's say the length of the input is 1,000 tokens. I mean, this is like a relatively small text, like let's say like 100 or like 1,000 words, or like, I know, yeah, something around that, 1,000 words. And this is like a relatively small context, and so it's something like 10 paragraphs or something, I would say. And the model can easily process this. And I think as we go down throughout these tree of the LLM calls, we of course get more asynchronous LLM calls, and this could be actually a good thing for the processing and regarding the GPU utilization and stuff. Because for example, if you have one node, let's say this is like the first call, and then it kind of spawns other children, and then they also spawn other children as well. And for example, here in this level you have almost like here, for example, in this example, we have 5 other prompts that they need to be processed and generate something. So you have 5 prompts to process. So instead of this huge context to be processed, you kind of break things down. You kind of look at it in a different, like in a recursive point of view. And I think now you can maybe batch all of these smaller requests, and if you just batch them together, then there's a chance that you get a higher throughput. So this could actually be really good even in the performance point of view. I mean, this actually could be really interesting, to be honest. Also from perspective of performance and utilization. Because the lowest level, I mean, like the leaves can be batched and processed at the same time. This would be comparable to processing the longer context. So basically, oops. So this would be like really interesting because you're breaking down your context, and usually when you process a long input, the thing is that the computation is really expensive on longer inputs, because they should create this attention matrices, and this should be calculated, and this is like the thing that is kind of expensive in a computation point of view. And if you break things down, so if you break things down, and for example here we have like 5 requests, yeah. These 5 requests, they of course have the lower input length, and they also, as you said, we can kind of batch them, like process them at the same time, and of course the output would also be relatively small. I mean, I have to think about it a little bit more, but kind of my gut feeling is that there's a chance that we kind of be able to push a little bit more into the utilization of the GPU, even for the one context, like one request, like a lower amount of requests. But of course, I think looking at the GPU utilization in just for a few requests, I think it doesn't really make sense. I mean, we have to look at it. We have to maybe look at it both when we are processing. For example, let's say we have 1,000 requests with really long context length, and we make a benchmark, like compare how much energy did this long requests use compared to if you use this recursive language model, and also how the utilization is going to look like. So these are the questions that, to be honest, would be interesting, and I'm kind of really interested in to have a look into this. Also, I think the craziest part, I mean, let me also copy this. Let me also write it down. I think the idea can be super interesting, especially in the context of this power consumption, and if you can really change anything in that matter. Okay. Yeah, I will leave it for now, but okay. Given an arbitrary length prompt using the string p, and RLM interacts with a persistent external environment. Also, I think this sigma star, I think this is something related to like this grammatics and computer science. So I think this basically means the string is part of the grammar. So basically this is kind of like a string defined in the language, or like this specific grammar. And RLM interacts with the persistent external environment and returns a response string. This will be a response string, and we would like effective unbounded input tokens, unbounded output tokens, and unbounded semantic horizon. Example, the ability to do omega p, omega p2 semantic work. Okay, to be honest, it's a little bit confusing for me, this part. Just highlight it. Unbounded semantic horizon. I mean, unbounded input tokens, they kind of make sense. We all have the k here. The k is the maximum context length, and we're saying that the unbounded output length and unbounded semantic horizon. I don't know really about this semantic horizon. So algorithm 1 describes how an RLM achieves this. Also unbounded output tokens. Given the prompt P, the RLM initializes a persistent REPL programming environment with a variable containing the user prompt as a string and a function for invoking a sub-RLM with a new prompt. Then it starts the RLM loop. In the first iteration, the algorithm invokes the root natural neural model M with only constant size. Metadata about the user prompt, like its length, short prefix, and how it accesses parts of it. The root is instructed via prompting. The root is instructed via prompting or fine-tuning to operate like an RLM. So prompting, fine-tuning to generate code that helps it understand and transform its parts of its prompt P and to build up an intermediate value and the final response into new variables, potentially by invoking the sub-RLM within loops. You can prompt it to do this, and existing LLMs can be prompted to do this, and that training an 8 billion model to be natively recursive is promising. Okay. Each iteration of the RLM loop executes code in the REPL updates. In the REPL updates REPL state, intermediate variable, and collects in stdout and printed text. Only constant size metadata about stdout, like a short prefix and length, is appended to M's history for the next iteration. So appended to M's history. RLM makes 3 simple design choices that are missing from existing scaffolds. To highlight these, we include algorithm 2 to illustrate a deceptively similar algorithm that is far less expressive. Also, let me... put a question mark here. Okay. Okay, so both algorithms support some notion of subcode, external objects, and code execution, but they differ in terms of where the prompt and intermediate values live and where recursion occurs. An RLM must give the underlying LLM a symbolic handle to the user prompt so that the model can manipulate it without copying text into the root context window. Okay. For next time, I continue here. Kind of had in mind to also have a look in the code. I'm not sure how much of it would be. Of course, it makes sense to first try to read reading the paper, getting some ideas, and then looking into the code. I think that would be like the best thing, but let me see. Okay, so open folder. Client's core, LLM handler, types, environments, constants, data. Okay. I think starting with prompts might be the easiest thing. The system prompt. Holy shit. Recursive LLMs as much as possible. Remember to explicitly answer the original query in your final answer. I mean, it's kind of trying to force it to use, like trying to guide it, instruct it to do the right thing. But of course, fine-tuning is also another approach if you want to do it. Yeah. It kind of gives so many hints. Okay, then I think I'm gonna keep it here for now. Also, I will move the paper here as well. So next time we can start. And yeah, I think the idea is really nice. I'm not sure how it's gonna really look when we start using it, or like trying to do some tests. But in any case, I think it's really in a good direction. Like, you're trying to process less context instead of just putting everything there, you know. I'm kind of hoping that it turns out to be something nice, or at least at the moment I already like the idea. And also, like, they are able to process 10 million tokens, so you're kind of doing something that no other language model can do, and you can do it with only like 8 billion parameter model. So I think this is really in a good direction. Of course, this is mostly related to the things that can be done. Let's put it this way, mainly towards the tasks that are kind of retrieval. Like, the task is to find this thing, or like what was the last thing that was said to blah 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 to this person, and this is the context, for example. Something in this direction, I think. And yeah, you can't really I mean, if you have such use cases, I'm thinking that this would be like really good direction. Okay, in any case, I think I'm gonna put a pause on things here, and next time, of course, we'll continue. I might also start with the like trying it actually in action. Maybe I get some Gemini API or something, and then try to play around with it a bit. But in general, I'm really looking forward to getting to read this paper a little bit more. To be honest, I think this is one of the papers that I was really excited to look into. Okay, in any case, I think that's it for today. Have a good day, have a good night, and hopefully next week we continue where we left off. All right, see you, bye.